Okay, I want to spend some time specifically on homogeneous systems of equations. And if you'll remember, a homogeneous system is one of the following. And if it helps as a mnemonic device or something, if you remember, a homogeneous differential equation was one. So homogeneous, say, second order linear homogeneous differential equation. Homogeneous was something where you had like y double prime plus y prime plus say y equals 0, right? The equals 0 part was why we called this a homogeneous differential equation. And if you remember, as soon as we started studying inhomogeneous differential equations, then all of a sudden this became some function of x, right? So it was something that was no longer 0. Well, this terminology is why we call these systems homogeneous, meaning they are all functions equal to 0. So a homogeneous system, for review here, would be something, if you would like it written compactly, where j goes from 1 to n. Let's say we have an m by n system, right? So this was aij x sub I equals b sub j. And then this was also for I goes from 1 through m, right? So we have this equation for each I. But here, for a system that's homogeneous, we have that b sub j, or b sub, I have these backwards, sorry. Because n is denoting the number of variables, and m is denoting the number of equations. And I is running from 1 to m, so that should be b sub I. Sorry for the mistake there. And a homogeneous system is when b sub I equals 0 for all I ranging from 1 to m, right? This is exactly what it means for a system to be homogeneous. Right, and so what this would look like represented as an augmented matrix is we would have our A11 all the way over to A1n, and then we would go A21 to A2n, and then AM1, AMN, et cetera, right? But then we just have zeros on the right-hand side of the augmentation. And I want to kind of try to understand or study solutions to these systems in particular, because for homogeneous systems, there's always what's known as a trivial solution. And that's never all that we're looking for. And in fact, it's usually not what we care about per se. It doesn't give us much information, but it's important to acknowledge it. So every homogeneous system has a trivial solution. And that solution would be, well, if you have a bunch of, if you have like a linear combination of variables, possibly multiplied by all these coefficients here, well, then if you have that all of those, the sum of all those is equal to 0, well, you would have a trivial solution if you just let each variable equal 0, right? This has a trivial solution of x sub 1 equals x sub 2 equals blah, blah, blah equals x sub n equals 0. Certainly that solves this system, right? 0 plus 0 plus 0, blah, blah, blah equals 0. You get that for every row. But we don't really obtain much information. And if this was to be in, say, in a physical setting, like we'll see some physics examples later, well, if we were to set up a homogeneous system of equations representing a physical system, learning that 0 equals 0 wouldn't do much in terms of our understanding of this system. So what we are interested in is finding the non-trivial solutions. So let's do an example of this. Let's look at a relatively small system of equations here. So we have 2x plus y minus z equals 0. And then we have x plus 2y minus 2z equals 0. This is a homogeneous system because all equations are equal to 0. And we can set up the augmented matrix representing this system by 2, 1, negative 1, 0, and then 1, 2, negative 2, 0, right? And we would wish to put this into first reduced row echelon form, right? So doing that, and maybe for the sake of time, so I can more in depth cover the physics examples. And I think we're comfortable now with computing reduced row echelon form of a matrix. You can see that this system would be, or this reduced row echelon form matrix would be 1, 0, 0, 0, and then 0, 1, negative 1, 0. And so once we have this, we see that, well, the first row corresponds to x equals 0. The second row corresponds to y minus z equals 0, right? And so we're going to have an infinite number of solutions here. This gives us the solutions x, y, z equals 0. And then let's say, well, we have y equals z here, which means we have a free variable, right? Let's say z is the free variable. So we'll say z equals t is our parameter representing the free variable. And so then our solution set would be the set of points 0, t, t for all t in the reals. So this would be a solution to this homogeneous system. And I wanted to cover an example or define a homogeneous system and cover an example of solving a homogeneous system still using our algorithm from the last video. And I wanted to use this example in particular because we have a different way of writing our solution. Like certainly this describes a solution set, which is great. But we have kind of a more formal way, or maybe more common when you have a parameter, is to write this as a vector. So let's write our answer in vector form. And how you would write this is you would say our solutions are the vectors x, y, z such that, well, then we have the vector 0, t, t, where t is a real number, right? We can write this, you know, we can scale vectors, right? That was one of the first things we learned in Calc 3 is like, whoa, well, vectors have a direction and a magnitude, and multiplying a vector by a scalar changes the magnitude, right? And so we know we can scale vectors. Well, every term or every component here has a t that can be factored out, right? So we have t, 0, 1, 1. We usually, when you have a parameter, this is usually how you will see the solution written. And I'm going to erase this intermediate step here. And maybe I'll just compactify. So 0, 1, 1. This is a much more common way of seeing how an answer with a parameter is written. It's certainly not wrong if you write it up here, right? That's what I've been doing up to this point. But now that we're starting to understand things more as an array of numbers, such as like vectors and matrices and things like this, we'll also start writing our answers in terms of these arrays of numbers, especially if you have a parameter here, right? And some notation will call, notice that all of the solutions to this system are just multiples of the vector 0, 1, 1. And so for that reason, we'll say 0, 1, 1 is the basic solution. So definition, right? In this context, all solutions to this system are just a multiple of that base vector. And this will make sense once we start to study vector spaces in the final week of class. You can actually build spaces based on, no pun intended, but based on basic solutions. And they form what's known as a basis. And so we want to start to kind of understand what a basic solution is doing now. We can kind of see how really any other solution is just this solution scaled or modified, right? And if you were to have something like, let's say we had a solution, just for an example, let's say we had a solution with 2 parameters. So maybe we had 2 free variables, right? Say we had like x equals something, and then y equals s, and z equals t, or something like this, right? Well, then your solution set would be like x, y, z equals, and then I'd like to use, well, it could be whatever, but how we would write it here is you would have this written in the same way, right? Here we found like a basic solution, and then we pulled out the parameter so that the parameter becomes like a scalar, and then the vector is constant. We would do the same thing if we worked through a question or a system that had a solution of 2 parameters, and you could get, like, I'll make something up, maybe like 1, 4, 3, and then like -1, 8, 5, or something like this. So let's say we had these 2 free variables. Well, then our basic vectors, or our basic solutions, are these vectors here, right? And we have a way of generalizing when you can write a vector as a combination of other like basic vectors here. And so that is a segue into this following definition here, which will be very important for the remainder of the course. So a vector, say V, is a linear combination of, let's say, I'm going to do capital X1. So note that these will be capital X1 through Xn, not to confuse with like the lowercase that we were using for variables. So a vector V is a linear combination of vectors X1 through Xn if there exists a scalar A sub I, or scalars A sub I for I going from 1 to n scalars, such that V is equal to A1 X1 plus A2 X2 plus et cetera, all the way up to A sub n X sub n, right? And here, I don't want the notation to take away from the understanding of the statement. So this backwards E here is read as there exists. It's kind of the sister symbol to the upside down A, the for all, right? Like for all something, there exists something. So you'll see a lot of the times like for all X, there exists Y, or something like this, right? And so that's what the backwards E means. And then, so we're saying there exists scalars, these A1, A2, all the way up to AN, such that V can be expressed as a linear combination of A1 times X1 plus A2 times X2. And that's exactly what we are looking at here. we're writing this as a linear combination of vectors. Like this would be x, y, z would be our v, 1, 3, 4 would be our capital X1, this would be our x2, and then our a1 would be the parameter s, and in this case, our a2 would be the parameter t, right? So just to kind of relate or to see what a linear combination looks like. And it's always a good question to ask. So here's a little example. Is the vector -18, 3, 2 a linear combination of the vectors -4, 1, 0 and -3, 0, 1? Well, so how do we know? If this -18, 3, 2 is a linear combination of the other two vectors, then that means there exists two scalars such that -18, 3, 2 is equal to, and this is what we don't know, right? This is what we're asking. Is this equal to, let's say, A times -4, 1, 0 plus B times -3, 0, 1. And now you're asked with like, well, is this do A and B exist, right? Well, you can, this one's relatively simple. It's almost by inspection. You can see that A would need to be 3 here, and B would need to be 2, because you'd have -12 minus 6 would give you -18 for the first entry. And then for the second entry, you would have 3 plus 0. And then for the second entry, you would have 0 plus 2, right? So yes, the answer is yes, because these constants are these scalars A and B do exist. And so -3, 0, 1. And so the answer is yes. We will see later how to, if you can't find this by inspection, because there's no reason that every single question like this would be something that you could just kind of figure it out in your head, right? You say, oh, well, how could I combine -4 and 3 and -3 to get -18, right? You're like, well, I could multiply -4 by 3 to get -12, et cetera, et cetera. You can kind of do that in your head for these simple examples, but we'll see in the future the process of, or we'll actually have kind of an algorithm to answering this question when it's not something that we can just solve by inspection. Okay. Now I want to quickly change gears and introduce a very important definition that we'll use through the rest of the course. So the rank of a matrix A is the number of non-zero leading entries for, or let's say of, it's the number of non-zero leading entries of any row echelon form matrix of A. Notice that I'm saying any because there are multiple row echelon forms for a given matrix. We denote this as rank of A, and that's read the rank of A, or sometimes rank A as just a shorthand here. And so calculating the rank has a lot of benefit once we start to study matrix theory in more depth. But for now, we're just going to define it and figure out how to calculate the rank of a matrix. So if we were looking at the matrix A, which is 1, 2, 3, 1, 5, 9, and 2, 4, 6, then let's say we want to find the rank of A. Well, how would we do this? we first need to get to a row echelon form of the matrix, or reduced row echelon form. It doesn't matter, right? Reduced row echelon form is a row echelon form of the matrix. It's just a reduced row echelon form. So let's get this into row echelon form here. So if you'll notice, the first thing I notice is that row 3 is equal to 2 times row 1. So we can immediately get a row of zeros by the operation that row 3 is equal to row 3, or kind of we're replacing row 3 with row 3 minus 2 times row 1. Well, then what that does is give us a row of zeros, right? Then what do we need to do next? Well, we need to get rid of, to put it in row echelon form, we need zeros below all pivot positions, right? So that means we need to get this to be a 0 next. And we can do that pretty easily as replacing row 2 with row 2 minus row 1. This gives us 1, 2, 3. And then for row 2, and we're going to have 1 minus 1 is 0. And then 5 minus 2 is 3. And then we'll have 9 minus 3 is 6, 0, 0, 0. To put this into a row echelon form, we have to divide any row that has a pivot position entry not equal to 1, right? So that means we need to divide, well, formally, the operation that we're going to perform is we're going to take row 2 and replace it with 1/3 row 2. This gives us 0, 1, 2, 0, 0, 0. And now we look at the number. What do we look at? We look at the number of non-zero leading entries for any row echelon form of matrix. Form of the matrix, excuse me. So for the first row, we have a leading entry of 1. So we count that. That's 1. And then we have a second leading entry of 2. For the third row, there are no non-zero leading entries. This implies that the rank of the matrix A is 2. And you'll notice, and we'll talk about this more in depth later. Like I said, we'll study the rank and its applications a lot more later, but I'll kind of tease this a little bit. It is not a mistake that the rank is the number of non-zero columns. If you'll notice, I'm going to erase up here what we've done. Kind of note the rank and the number of non-zero columns, rows, excuse me. These are both 2. And I'll kind of spoil some theorems in later material, but this is not a mistake. Okay. I want to finish our talk of homogeneous systems and rank with one theorem. And this is the last we'll talk of rank for a little bit. So if, and sorry for the poor handwriting, if an M by N matrix A represents a system. Well, let's first say that this matrix A has rank R, then the number of free variables or parameters of the solution set of the corresponding system is n minus r. So this makes sense. We can almost do a proof by, we can almost do a proof by inspection here, right? Because if n is, in this case, n was 3, well, the number of free variables is going to be the number of all 0 rows that you have, right? And so here we have 1 row of all zeros, and then, so that means we would have 1 free variable. And then the rank was 2, right? And so we would only have 1 free variable, if that makes sense, right? Basically, what this n minus r is saying is, well, if the rank gives you the number of non-zero rows, well, then n minus r gives you the number of 0 rows, right? So that's basically what this theorem is stating. Okay, so I think because this video's gone slightly longer than I wanted, what I'm going to do is in a much shorter video, I will include the physics or the, I have a chemistry application that I want to talk about and a physics application that I want to talk about of the stuff we've been learning from this first chapter. So because this video's gone a little long, I think I'll break here and then discuss the applications in the next video.